In order to do calculus on surfaces, it's going to be necessary for us to be able to parameterize those surfaces. So let's spend a few videos talking about how to parameterize surfaces. The first case is going to be a fairly easy case. And that's going to be parametrizing the graphs of functions. And that's going to be using rectangular coordinates. Now, when I say that I'm parametrizing the graph of a function, I mean that I'm going to be able to explicitly write z as a function of x and y, or maybe x as a function of y and z, or maybe y as a function of x and z. Now, in each case, since I'm parameterizing a surface, I'm going to be able to use two parameters. For now, let's call those parameters u and v. If z is a function of x and y, I can set x equal to u, y equal to v, and then z will be f of u and v. And then notice that all three variables, x, y, and z, are written in terms of u and v. For surfaces, I often call my parameterizations phi. So I'd say that phi of u and v was equal to u, v, and f of u and v. So just as we had one parameter when we were talking about a one-dimensional object, a curve, we're going to have two parameters when we're parametrizing a surface. In this case, when x is equal to a function of y and z, I can set y equal to u and z equal to v, and then substitute into g to get x, giving me the parameterization phi of u and v equals g of u and v, and then u, and then v. And I bet you can guess what's going to happen over here if y is a function of x and z. This time I can let x equal u, z equal v, and then y is going to be h of u and v. So my parameterization looks like phi of u and v equals u, h of u and v, and v. So let's look at a bunch of examples. Suppose I wanted to parameterize z equals x squared plus y squared. Well, here notice that z is already given as a function of x and y. So I can let x equal u, y equal v, and z will be u squared plus v squared. Using the phi notation, I'll say that phi of u and v is u, v, u squared plus v squared. As a second example, suppose we want to parameterize the plane that has equation 2x plus y plus 4z equals 12. Well, here we don't explicitly have one variable written in terms of the others, so we'll have to solve. Now, it's going to be easiest to solve for y, because we won't end up with any fractions. So here's one possibility. I could write y equals 12 minus 2x minus 4z. And then for my parameterization, I could let x equal u and z equal v, and then y will be 12 minus 2u minus 4v. So that gives me the parameterization phi of u and v equals u 12 minus 2u minus 4v, comma, v. But I also could have parameterized this by solving for a different variable. For example, I could have solved for, say, x in terms of y and z. So 2x is 12 minus y minus 4z. So dividing by 2, x equals 6 minus 1/2 y minus 2z. So x is written in terms of y and z. So that means I'll set y equal to u and z equal to v, and x will be 6 minus 1/2 u minus 2v. Or using the phi notation, phi of u and v is equal to 6 minus 1/2 u minus 2v, comma, u, comma, v.